So let me start what origami is. Now, origami is an international word, so operation itself, or sheet of paper, or the art of paper folding. So the use of origami is recorded. So before 10th century already in Japan, the people in the court, aristocrats, are using origami to symbolize their feelings and thoughts without explicitly saying what they want to say. But the change occurred in the 19th century when some people argued that origami can be used as a tool to teach mathematics. So the formalizing origami started in the middle of the 19th century, all until 20th century. As you see, construction tools of origami is just folding. You cannot do arbitrary folding. You have to obey certain rules. There is a rule called Fujita Justin. This is used as a base for mathematical theory of origami. In the case of Euclidean geometry, it's circle and lines. In the case of origami, it's just fold lines. So the points of origami are strictly larger than the set of points that Euclidean geometry with Euclidean tools can generate. And one example would be is that construction of trisector. Trisector of an arbitrary angle has been a long-standing problem until 18th century. But origami, you can do it. So I would like to show how to do it. It's just several lines of Orikoto programming language. Orikoto language has an implementation of the Fujita Justin rules, which is the base of mathematical theory of origami. There are 7 rules, and one is, if you look at PN2, the fold along the line that passes through PN2. And the other is a superposition of the given object. So for instance, this one is that you are given 2 points, you are allowed to superpose 2 and folding along the line that is defined by this. And if you unfold it, you will have what we call fold line, or sometimes called crease. 4, 5, and 6 are more involved. This rule, which says that given 2 lines and 2 points, to superpose 1 point, 1 line, and the other point, the other line. And you don't need to do a special computation. Our system starts implementing this Fujita Justin rules. It is 7 rules, but you can define this 7 rules in one function. So we call HO later in my program. So in addition to this Fujita Justin rules, we need a lot of auxiliary functions to make origami. So we start with your session first and create an origami of certain size. Then I want to put a point any place, but since I defined this origami 10 by 10, I put E here by specifying the coordinates of it. So what I want to do is to trisect this angle. And in order to trisect, we need 2 parallel lines. And how do I make 2 parallel lines? And also that parallel line should be parallel to this baseline. It is very easy because our O2 rule simply says that if you bring A to D, and bring back, exclamation mark is a postfix operator of unfolds. And similarly, you get this HI by bringing A to F. And we are almost done for trisecting this angle. The secret is that we use this O6 rule to put point P on E, A on HI. Surprisingly, it gives you three possibilities. This time interested in trisecting this part, this angle, we take that one. So then fold it using number 3. We get this one, right? And we are almost done because the line that passes through here and there will be a trisector. To make it nicer, I project those points, do a new name, and here we go. You have K and J. K, A, and K, J, A are trisectors. Okay, so we are done. Long-standing problem is solved. Next thing is, are you sure? In order to do that, we need to tell the system what we should prove. So our verifier is based on equational reasoning. For equations, we have to have equations among polynomials, so we have to have polynomials. Ideally, we want to say that 3 angles are the same, but these angles are difficult to handle in equation settings. So we have to take those angle equalities into polynomial equalities. These are kind of transformations. Afterwards, we make it a general one. So let ABCD be a unit square and E to be arbitrary and prove it. And the system checks whether the equations that are generated from the programs are polynomial equalities. And if I click this, proof document is generated. So one interesting example of this trisection is Morrell's triangle. So give an arbitrary triangle, and you trisect each inner angle and pick up the intersecting point of neighboring trisectors, and you get this tiny, and this triangle in this case is an equilateral triangle. So this is one nice example of how trisection is used in origami. Traditional origami has a lot more materials in it. The base is very simple. You have a valley fold and mountain fold. The reason why it is mountain valley is, well, if you look at this is quite obvious. If you make a fold like this, then this line looks like the path in the valley. And if you do opposite fold, then this become a mountain ridge. So these two are the most basic, and this could be actually in computer implementation. It is one realization of fold operation, so it is carry the function. So you need one more argument to make this valley fold work. Valley fold produce something visual. And there are some more interesting ones inside the reverse fold. This is inside the reverse fold. If you look this way, then you will see that it looks like one fold, but one part is mountain fold and the other side is valley fold. And we take this as a single fold. And the other one is this one, outside reverse. The inside or the opposite is outside. So you get this one, and you will see here the mountain fold and valley folds. And there are one more, which is quite often used as a squash fold. So suppose you were given this, and squash fold is to squash this part into here. If you look this one, then it's quite obvious. this puzzle is forced into here